All right, thinking about our second class of reactions here, we have hydration reactions. Now think about what hydration means to you. Adding water, right? You always hear stay hydrated, stay hydrated. Well, stay hydrated. Let's add water across the double bond. There are three different ways to add water across the double bond. The first one that we will investigate is called acid catalyzed hydration. This is very, very similar to our previous reaction of hydrohalogenation. We have a reactive acid, H3O+, and we are going to be using that to catalyze the hydration reaction of adding water. Sometimes over this reaction arrow, you'll see H2O with H+. That's understood that we're having an acid with water. Or you can even see dilute H2SO4. Dilute meaning water, H2SO4. Remember when H2O and H2SO4 get together, that is a formation of H3O+ and HSO4 minus 1. This reaction is very, very good because we can think about the pKa of H2SO4 being -7 and the pKa of H3O+ being -1.7. So again, less reactive, more stable conjugate acid, we favor forming H3O+. I'll always use H3O+, but it's good to note that there are other reagents that mean the exact same thing. We just got to kind of rack our brains with understanding what those reagents mean and how do we form H3O+ in multiple different ways. Oxymercuration and demercuration, we are going to see it's another way of adding water across that double bond with using a mercury style catalyst, followed by a reduction reaction with sodium borohydride, NaBH4. This is a good reaction to just kind of understand and know. We'll see part of the mechanism, but not all of it. And that's just primarily because oxymercuration is what I call the call for a change in the carbocation intermediate. So we'll see a carbocation intermediate with our first acid catalyzed hydration reaction, but then we'll see some problems with that carbocation intermediate. And so we want to mitigate that and have an option for a non-carbocation intermediate reaction. Hydroboration oxidation is another way. This is going to be an interesting look at when we get into the specific reactions. We'll see that this is a concerted style reaction, so no intermediates for that first step when we actually think about the placement of OH and H across that double bond. Let's start with acid catalyzed hydration. I really want us to hone in on the similarities between our previous reaction, which was hydrohalogenation. We'll start with a proton transfer. Again, just like hydrohalogenation, we had HBr or HCl. Those are very good acids. H3O+ is still a very, very good acid. Again, regioselective here for the rate determining step. Because we are reacting our alkene to form a carbocation, that carbocation will go on the more substituted position. So we are doing Markovnikov addition. Excellent. Second step is going to be our nucleophilic attack, just like previously in hydrohalogenation. Water is the functioning nucleophile here, right? We can see that water was our nucleophile in SN1 reactions as well in chapter 7. Not stereoselective. Reason for the idea of not stereoselective is because that carbocation, again, has a top side and a bottom side. So when we think about water being able to attack, it can attack either from the top or it can attack from the bottom. So we will get racemic mixtures if we form chiral centers. So we have this oxonium ion intermediate. We have an extra third cleanup step. Similar to our SN1 reactions, we need to do a final proton transfer so that we get a nice neutral alcohol final product. Excellent. So here again, another beautiful diagram of understanding that this is not stereoselective. We will get all different kinds of stereoisomers to form in this reaction. Just to introduce one of the main problems with carbocation intermediates before we get to our alternates, we'll do one more mechanism here, proton transfer. Let's make that carbocation. If we're looking at carbon 1 versus carbon 2 here, carbon 2 is more suited to hold that carbocation because it's a secondary. Now, just like in all of the carbocation intermediate reactions before us, secondary carbocations can rearrange if there's something more stable nearby. So here's one of the biggest issues with carbocation intermediates is that rearrangements occur. Markovnikov addition, we want to try to find the best region to put that carbon positive charge. And so we will do a 1,2 hydride shift and then continue on with our nucleophilic attack. Again, that nucleophilic attack, attacking the carbocation. If a chiral center were to form, we would see that a racemic mixture would also be forming, so two products. In this specific example, we don't have a chiral center. So we are good to keep going on with our cleanup step to make our final alcohol product. There we go. So regioselective, carbocation has to be the most stable. The oxygen is going on the most substituted position. Just remember, carbocation rearrangements are valid always. Not stereoselective. If we were to make chiral centers, we would get racemic mixtures. Now, the oxymercuration demercuration reaction is the answer to the carbocation problem that we just saw. So the oxymercuration reaction, I'm going to throw up a specific example here, uses a mercuric acetate, HgOAC2, and water. Now that water can change, it can be any alcohol, and we'll see different variations in class with that. Water is the most common, and that's when we would add OH and H across the double bond. But again, if you added an alcohol, it'd be an H and the rest of that alcohol across the double bond. What we get out of this reaction is very unique. We get OH on the more substituted side of the double bond, but notice how there was no carbocation intermediate. We could have predicted that if there was a carbocation intermediate, there might have been a carbocation rearrangement here to the more substituted position next door, that tertiary instead of the secondary carbocation. Let's dive into this mechanism just to be able to see why we have no carbocation rearrangement here. Just to give you an idea, OAC minus 1 is going to be utilized in this reaction. AC is really the acetate anion. This is a stabilized by resonance anion. We've seen this guy before in our SN2 reactions. And so we'll see him again. OAC, though, is acetate. So I'm going to use that abbreviation for us. Now, mercuric acetate is a very interesting reagent that actually reacts with itself first in order to make the electrophile. Now, again, OAC will leave. That is stabilized by resonance. This is our electrophile that we can use in the first step of this reaction. Notice it's not an acid, it's an electrophile. So our nucleophile, our pi bond, is no longer looked at as a base, it's now a nucleophile. So here we go. Let's write the rest of this mechanism here. We have our carbon attack, or our carbon-carbon pi bond attack the mercury. And we start to imagine forming a carbon with a positive charge, but what really actually happens is mercury will start to use its large size and do what we are going to call back bonding. We're going to make a bridge with that mercury. Think about where mercury is on the periodic table. Mercury is in the transition metals group. It's in the D block of the transition metals. It's large. It's in row 6 of the periodic table. And so it's relatively big. It's also a metal, so having a positive charge on it is not something that would be too shocking for us. We think about metals, we think about them being able to have that positive charge on them. Now, what this creates is a bridged intermediate, and that bridged intermediate is going to be attacked by water. Now, where that water will attack is still Markovnikov addition. If we think about this attack right here, water is not a good nucleophile. We called it a weak nucleophile before. So it still will attack the more substituted position because as it does so, it is slow. We'll get water to attach on that more substituted position, and we'll get that mercury to kick open the bridge. Now, this is as far as we need to really be able to understand the idea of the mechanism itself. But just note that that NABH4 second step is going to be a pseudo cleanup step. We'll see what it does later. But at the end of the day, what we are going to make is a product where the OH is on the more substituted position, but no carbocations can form. We still get racemic mixtures. So in chiral centers, we will form both the R and the S. So not stereoselective. Definitely regioselective, but not the same regioselectivity as a carbocation intermediate, but still regioselective. Oxygen is getting on the more substituted center, but no rearrangements are possible.